Welcome, gentlemen, to an introduction to the mole. This is a brand new unit, but I think it is one that you will grasp quickly because it's pretty relative to experiences you've already had. One of the first similes, I guess it is, that your book uses is the dozen. There are a dozen objects, 12 objects in a dozen. It's always 12 objects in a dozen. So if I had 3 dozen donuts, I would have 36 donuts. If I had 4.5 dozen donuts, I would have 54 donuts. We all know how to do the math on those kind of things. It's pretty simple. And that is basically what I'm about to tell you right now. Is it says a slightly different number. A ream of paper is 250 sheets of paper. A gross is 144 objects, that kind of thing. So it's a concept that you're pretty familiar with, and I'm going to expand on it a little bit here and help you understand it. There was a guy, a person, named Amedeo Avogadro, way back in the day. As you could probably tell, he's Italian, and he worked with gases, and we'll talk more about him later when we actually study gases. But he was very important in our study of the mole, and with his work with the mole, he determined that a mole, and using gases he came up with this, that a mole is an amount of objects equal to 6.022 times 10 to the 23rd of those objects. So it's actually a longer number than that. We just rounded to 4 places. So if I had 6.022 times 10 to the 23rd objects, I would have a mole of those objects. It would be very difficult to have a mole of moles, because moles are pretty small, but nonetheless, a mole of moles, 6.022 times 10 to the 23rd moles, that's a lot of moles. Good one. A mole of marshmallows, the big marshmallows, the ones you put one on a s'more for. A mole of marshmallows, 6.022 times 10 to the 23rd marshmallows. If we made a blanket of marshmallows, a mole of marshmallows over the United States, it would form a layer of marshmallows 8 miles thick above, covering the United States. That's a mole of marshmallows. Imagine an 8-mile covering of the United States, straight up with marshmallows. That, gentlemen, is a lot of marshmallows. If we had a mole of pennies, 6.022 times 10 to the 23rd pennies, and we divided those pennies equally, we'll say there's 7 billion people on the earth. If we divided those pennies equally among everyone on the earth, every person on the earth would have $360 a second to spend for 75 years, assuming everyone lived to be 75 years old. That's a lot of pennies. Imagine that from the instant a person was born until they died at the age of 75, through 75 years, that would be $360 a second. Money would be worthless, wouldn't it, if we had a mole of pennies to our disposal? It's kind of crazy, isn't it? It's a lot of money. If you drank a mole of soda, lads, here's the deal. It would be just like a regular sip, That's how much a mole of soda, 6.022 times 10 to the 23rd particles of soda, be it diet, regular, iced tea, coffee, whatever beverage, right? It's a sip that probably really wouldn't even refresh you. It's so small. And the whole reason I tell you that is to let you know that a mole of molecules is pretty small, especially something like water. Well, all molecules are very small. So while $360 a second for 75 years and an 8-mile deep blanket of marshmallows over the United States is impressive, a mole of soda really isn't that impressive. Every time I see this picture, it hurts. My, oh my, oh my. Regardless. Now, a mole of anything, 6.022 times 10 to the 23rd particles of it. So, a mole of neon. There would be 6.022 times 10 to the 23rd atoms of neon in a mole of neon. Hydrogen, 6.022 times 10 to the 23rd molecules. Remember, it's H2 here, right? H2. Mole of tungsten, 6.022 times 10 to the 23rd tungsten atoms. How about methane? A mole of methane, 6.022 times 10 to the 23rd molecules of methane. Now, here's a little bit of a snapper. There are 5 atoms in each molecule of methane, right? So 1 carbon, 4 hydrogens, there are 5 molecules, tetrahedral. Remember all that, right? Good. So therefore, I have 3.011 times 10 to the 24th atoms in 1 mole of methane. Ponder that. And most people figure out all I need to do is multiply that by 5, and I get that number right there. Okay. Now, how does this work? Well, very simply. We have a problem. How many moles are found in 1.334 times 10 to the 22nd atoms of silicon? Good question, Mr. Nolan, good question. Well, lads, let me show you how to set it up. All right? So, what do we got? We've got 1.334 times 10 to the 22nd atoms of silicon. Notice I'm labeling things, right? And I know that 1 mole of silicon is 6.022 times 10 to the 23rd atoms of silicon. By the way, this number here, 6.022 times 10 to the 23rd, is called Avogadro's number. Named after Avogadro. Avogadro's number. So ultimately what this comes down to, if we think of this as being a fraction, we've done this before. We've got atoms in the numerator here. We've got atoms in the denominator over here. Atoms of silicon cancel. And it becomes a division problem. 1.334 times 10 to the 22nd divided by 6.022 times 10 to the 23rd. And we end up with 0.02215 moles of silicon. Notice, lads, I've labeled everything. Everything has been labeled. Not just atoms. Atoms of what? Not just moles. Moles of what? Now, notice, the answer is moles of silicon. When I set these up, whatever is in the numerator up here ultimately will become our units over here, because whatever is here cancels from whatever is across from there. So 0.02215 moles of silicon are found in 1.334 times 10 to the 22nd atoms of silicon. How many atoms are found in 12.62 moles of xenon? Or as the Brits would say, xenon. Well, let's set it up. We have 12.62 moles of xenon. I've got Avogadro's number, 6.022 times 10 to the 23rd atoms of xenon over 1 mole of xenon. Moles of xenon cancel. And I end up with the number of 7.600 times 10 to the 24th atoms of xenon. A little bit of rounding thing in there, but that's okay. We'll work more on that. So 7.600 times 10 to the 24th atoms of xenon. How many atoms are found in 125.8 moles of water, H2O? Well, remember now, atoms, not molecules, atoms. So I've got 2 hydrogens, 1 oxygen, so there are 3 atoms per molecule, right? So let's see how we can set this one up. A little bit more interesting. Okay, we start with our 125.8 moles of water. We convert it to molecules by having 6.022, Avogadro's number, times 10 to the 23rd molecules of water over 1 mole of water. Moles cancel. Notice now our units are molecules of water. And there are 3 atoms, H, 2 H's, and 1 O in 1 molecule of water. So molecules of water cancel. My units are atoms. And my final answer is 2.273 times 10 to the 26th atoms in 125.8 moles of water. Fascinating, huh? Pretty good. All right. Let's move on. Okay, your turn. I'm just going to put down the answers. I forgot an O there. Oh, no, I forgot my O. How many atoms are found in 1.11 moles of copper? Hit pause, do some work. I'll be right back with the answer. That's what I got. Check your work. Next one. Here comes the answer. Did you get it? I hope so. Oh, that's an E. Sorry. Hope so. Here's another one. Here comes the answer. Hopefully you got it within rounding. All right, I got one more for you. And we're not going to answer this one home. This is a bit of a, or until we get to school on Monday. This is a bit of a snapper. All right, so check this out. Here's a ponderable. An atom of platinum has a mass of 195.09 AMUs. Now, 1 AMU has a mass of 1.661 times 10 to the negative 24th grams. What is the mass in grams of 1 mole of platinum? Bring your answer to class on Monday. Thank you, lads. Have a great weekend, and I'll see you in class on Monday.